And thanks Arena for bringing me all the way here to come to a class which is similar to the one I've just done last semester. So it reminded me of my last semester teaching. So great to see many of you here, and good morning to you. I've got a lot of things to cover today, and these are really just primers for you to think about. If you want to go in depth, there are quite a lot of publications that we've done in the areas that I'm going to mention to you now. They are all available on our website, which is at the top here. Also, there is an email somewhere for me. If you need any help or anything like that, just contact me. So quite a lot of things to cover, and I only picked up a few things that I felt will be of importance to you here as scholars and as somebody who is interested in energy. So if I start first by giving you some geography lesson. So in the Southampton, this is the UK, this is Ireland, this is France, this is Southampton here, which is really the Riviera, or basically the tropical side of the UK. Our temperatures are the best one around in the UK. This is Isle of Wight. I'll talk a little bit about the Isle of Wight in my talk. And this is the English, this is the Solent, you call it here, and this is France. So you get ferries across from Southampton and Portsmouth to France and so forth. So that gives you a bit of geography where Southampton is, an hour and 20 minutes from London. And that's the reason I selected it, because I want to be closer to London, but not in London, so I can study. If I stayed in London, I probably would have lost it, and I'll never be here with you today. So there you go. So this is all about Southampton, where it is. And we have also a video which is done by one of my teams to actually look at what we do across the whole divide in terms of energy and energy efficiency. I'll just play that for you. There's no sound to it, I'm afraid. It's not working. So those are areas that we're actually doing a lot of work in. So there are various groups in Southampton, but I'll be really talking to you about what I've been doing in my group, with my group. And the dean will like me to show that as well, so there you go. Okay. So if I start by talking to you about something that you probably know, which is about renewable energy, and I just picked up these areas, basically the solar radiation, geothermal, and gravitational motion, because they have got an impact on what I'm going to talk to you about today. And if you look at the gravitational orbital motion, basically the moon and the earth, you've got the tides, so you can convert the tides using turbines, flow in the water. I'll talk about that later on. You can get the geothermal energy, basically you get heat. And here in Southampton, we have the only geothermal plant giving you space heating for the city centre. And then you've got the solar radiation, which gives you the photosynthesis, biofuels, kinetic energy, wave, and wind, which I'm going to talk something about that as well. And then we look at latent heat, potential energy, hydropower coming from that, and also what's called sensible heats, and solar radiation, solar thermal, solar photovoltaics. So, a little bit about the resource and the variation of the resource. So you've got this map, and I think you're aware of this, in relation to amount of energy you get per meter square per annum. And the solar resource is made of two things, basically the diffused and the direct. And you can see this is Aden, where I come from. You got a lot of direct light, got less of a diffused light. And this is London, and you can see you got more of the diffused and direct light. So this is an area of research for materials. Okay, for example, in European countries we have more of the diffused. You could have the encapsulating material for photovoltaics to take more of the diffused light rather than direct light. And how much do you pay for this, and how much energy you get out of it? These are UK prices. For a kilowatt peak, you pay about £1,500, 9 square meters. And how much energy it generates? This is what you get from roughly 1,000 kilowatt hours per kilowatt peak. In fact, it's about 820. And that will power up, a kilowatt peak will power up about 1/4 of the energy for a house. But if you go down to the regions which are more intensive, like here as well, you probably get more than us by capacity factor of about 30%. So why am I talking about this? Is really in relation to utilizing photovoltaics, what's called micro generations in our buildings. You bring the energy source and the energy conversion to the user and make them perhaps change their behavior. And this is a graphics to show what we're trying to work at: ground source heat pumps, wind turbines, solar photovoltaics, and also look at the insulation of the house and so forth. So in relation to photovoltaics, you can have different ways of integrating these systems. You can have bolt-on systems on top of the roof. You can have roof integration. You can have cladding, like here. You can have facade glazing, and you can have PV shading, and you can also have some atria or perhaps skylights and so forth. I'm mentioning this because I'll be talking about that, because it's one of the solutions we have to come up with in the UK for our university. Integration, we also developed some roof tiles within my group to look at those. But the most important thing is that in the UK we have a regulation saying by 2016 all the new buildings, all the new homes should be zero carbon. And you can only achieve this by two ways. The first one is by making the building generate its own power, or the second one, which is cheating, you can actually get the power from somewhere else, from wind turbines. Okay? So the essence of that law is that, for me, is that the buildings themselves generate their own power, but now there is a lot of cheats around to say, but we are actually importing it from somewhere else. Okay? So here's the bit about the atrium that I'm going to talk about. I said you bring energy to the user, so electricity generating at the point of use, obtain the full value of electricity, you avoid the imports, you can export if you wanted to, you get feed-in tariffs, and then you have a multifunctional element, if you like, in the features that I'm going to talk about. And there is an added value, technology, environmental statement. For example, the university, you got people around in this fantastic space and say, here we are, it's our statement, we are green. And you got a lifetime of about 30 years guarantee for it. It's a high capital cost and the low power density, which I mentioned before. There is also something else in relation to building integrated photovoltaics, which you have not mentioned here. Can anybody tell me what it is? Something very mean. Why are we having building integrated photovoltaics? Okay. The reason building integrated photovoltaics came about is that the Japanese started about 2000, I think, and then the Germans came up and did that. Is that part of the photovoltaic system as a standalone, you have to have a battery storage. And if you take away that battery storage, it's a third of the cost. So you use the grid as your backup, right? So you reduce the cost, and therefore you expand the market for photovoltaics. And that's really the reason people actually thought about having photovoltaics in buildings, is to knock down the cost and allow expansion of the market. So here's the building I was going to mention and talk about at length. Here's the building from the top. This is the roof tile that we have done, and this is actually a bet in the conference. I went to a conference, I think in Switzerland, and the company who I think was part of Siemens, they had a roof tile which is about a meter length, meter 1.2 by about 80 centimeters, and it's integrated within the roof, has got this all integrating structure and so forth. It took me around, he looked after me and all and so forth. We went and had a discussion, and I said, I bet within 2 years I'll come up with a better system than this. They are colleagues, they are academics, so they're colleagues, so they're not worried about it. And the reason for it is that you have got hundreds of years of roofers. You don't want to retrain. Okay, what you want to do is to give them something that they could use as a roof tile or a shingle if you're coming from the States. Okay, so this is, oops. So this is what we came up with. You have a structure, you have it in there, and basically when these are the roof tiles that they have in there, and that structure becomes part of the roofer. Comes in and does all the roofing and just use that structure as part of the element. So basically replacing one concrete tile or planar tile. And then the photovoltaic element is basically a glass component with a push fit and 2 connectors like that. Okay, so we spend millions, actually the company who we gave the patent to spend millions to do it. And then unfortunately the price was higher, and they don't know very much about photovoltaics. It's a really sad story. It did not fly because everybody else in the UK, because of the feed-in tariff, had bolt-on system, which is about 2/3 the cost of our system here. Okay, so let's talk now about something which actually did succeed, which is glazing. So this is the atrium that I mentioned early on. University wanted to do is actually envelop this type of the administration building. As you know, administration got a lot of power, so anything you do with their building, they're very important people, so you need to be very careful. These used to be domestic homes around here, around this area, and this is the plan by the architect to actually allow us to build another building, which is this side here. And they wanted to maximize the space for utilization. It's actually called a student services building now here. And we said that an atrium would be really quite nice to have. The architect was very worried about the solar gain you get in the atrium. And he said that means you need to have some shading, you need to have some curtains, you need to have blinds, a lot of problems with maintenance and so forth. Said, no, you don't need to have this. Why do you have photovoltaics instead of that? So that's basically, so we did quite a lot of analysis in terms of airflow. We did monitor these offices and so forth. This building also have ground source heat pumps coming out from there. So cooling out there and also cooling out this side of the building. So that's looking at this glazing. Those of you with sharp eyesight, you can see that the separation between the cells is decreasing as you go up. So it's a bespoke element, and the reason for it is that you need to design to allow quite a lot of the light to go into the other building which is facing it. Okay, so it's photovoltaics, but also got architectural design and also shading and so. So that's why we call it a multifunctional element. So remember, this is done in 2005. So all the costs I'm going to tell you as an example. I thought if I mentioned this to you because it may relate to something that you want to do here. And this is what you need to do if you actually have an atrium like this. You can have an internal shading, integrated shading, or an external shading. All these have different functions, capital costs and operating costs. So if you look at an auto roller blinds, you have very nice shading here. Roller blinds is something you pull down, and the cost per square meter is that amount, and you have a per annum operating costs of about £17.5 per square meter. So these are called manual blinds. And then if you look at high glazed low E values, the cost for that is about £450 per square meter. So what you need to do is to see where you can replace this. So if you look at other option, which is external, which is track lameller, and this is the cost, and this is the operating costs. You can also have a fixed lameller, which actually is much reduced, about half the price, and you got the operating cost per annum. If you look in terms of photovoltaics, okay, to replace external or internal, you can see that the cost is actually almost the same the cost as the double glaze, because you get replace the whole lot. Slightly less than that, to be frank with you. And because you are producing power, you're actually gaining income, okay, because of feed-in tariff, or you're displacing kilowatt hours that you are importing. So looking at this, so this is basically looking at the capital cost and the annual cost. You got this graph in here, and for our operating cost, what we done in our analysis, this is the paper here, if you look at it, we looked at the PV system inspection, the inverter repair, basically main time to failure, 10 years, she changes her, and then you got an income from the rocks, is about, at the time, is about 4p kilowatt hour. And then you add that, if you generate kilowatt hour, you displace a kilowatt hour, you add the cost into that. So this is where our solution, at the time 2005, basically negative annual cost, it's about £480. So what happens if you compare it to other, so this is monocrystalline photovoltaic 2008 cost. If you compare it to other costs, for example, the external lamella, which is this one here, you can see the operating cost pushes up there. And if you look at costs which are 2020, photovoltaic 2020, you can see the cost will be about £100, actually is at the moment that cost today because of a drop in photovoltaics. Remember, we did that in 2005. And if you have what's called glass frit, basically glass which is actually slightly opaque, instead of having photovoltaics, it's very cheap and you don't really need to maintain it. So we did some analysis for this, and if you don't have to borrow the money for the PV, you can see you start with about £500, and then because you're getting money at 4p kilowatt hour, you can see you're getting income. If you have to borrow it at 5%, 2005 cost, then you never achieve your target. Okay. Then we did that for the internal roller. We did that also for the blinds that we have, and you can see for both of them, the cost is actually going up because you have maintenance cost. And if you add to it the external lamellas that you have in there, again you can see it's actually worse than photovoltaics. Question?
Can you just repeat the OPEX cost of -3? How do you come?
If you generate from photovoltaics 1 kilowatt hour, you get a feed-in tariff, okay, and you also get a displacement of the imported kilowatt hours. So if you are importing at 10 pence a kilowatt hour, and you're getting a ROC of 4p, basically the income you gain is about 14 pence a kilowatt hour. And you add that into your element of analysis. You're displacing import, but you're also getting funding through the feed-in tariff. So you add that as being something that you put that in your costs.
And maintenance is minimal.
And the maintenance is just the rain. Rainwater cleans it, and that's it. We have not maintained it since 2005. We also got other project which is actually vertical facades in the university, 1997. We have not even touched it with a cloth at all. So just basically, because the UK is wet, the rain actually cleans out for you. And there is not much degradation in relation to coverage and things like that. We haven't actually seen very much. Anybody else have a question? I should have asked this. If you want to stop me, ask a question, please do so. Okay, so this I felt this will be quite important for you to think about in relation to this region, because I know you don't have a feed-in tariff, but maybe in the future you may have feed-in tariff. But you have things that are like solar gain, and if you have various components like glazing for this iconic hotel, you know what hotel is this? Jumeirah Beach Hotel. So we have a paper. Unfortunately, I didn't put it in here, which is actually looking at photovoltaic and arid regions. So this is the iconic hotel that we took in our simulation. We did the thermal analysis of the whole building, and utilizing different technologies, that are in here. I'll show a graphic of it. And this is thin film solar and comparing them with it. So here's the graphic. So this is the predicted room cooling load, okay, in kilowatt hours per annum. This is the current load because you got low E glazing. You see it's about 6,500 kilowatt hours per annum, per square meter. I think it should be that. No, actually for the whole, is it for that, for the whole lot? Yeah. If you go for a low glaze at 85% transparency, then you go down even further in terms of the cooling load. And these are the other technologies that you can actually employ. The aerogel, which I showed a photograph of that, and so forth. If you go into electrochromic, which is what you have now in the Dreamliner. Anybody went in the Dreamliner aeroplane? The Dreamliner, they have electrochromic windows. Basically, you apply a voltage to it and it goes darker. And you can see you can actually reduce your cooling loads by about half in that. If you go to thin film photovoltaics, remember this is 2005 analysis. So you got 40% transparency of thin film technology without generating power. Just replacing the old glaze is much better. So it's gone down from 6,500 to 500. If you generate power and you're getting money for it at 4 pence a kilowatt hour, you actually reduce the cost even further. And this is the thin film, what we anticipate the cost will be about $1 a watt by 2020. And this is where you get further reduction. What happens if you generate power? This is where you get an income generation for the hotel, and therefore a reduction in your cooling loads. Okay, so another opportunity to think about.
Can you explain in this graph, how do you relate the cooling load to the income generation? That's something I've
The cooling load, the income generation is really money that you can, the cooling load is money that you spend to cool down the buildings because you're importing electricity. If you displace that cooling load with electricity generated on site, that's the income.
But your access is in kilowatt hours.
In kilowatt hours, yes.
So there is no revenue. So what you're saying is basically you can actually cool your building just by the facade.
By the facade, yes.
And
but
you get extra.
You get extra, yeah.
Which building are you referring in this one?
This building here.
In Dubai.
Jumeirah Beach Hotel.
I would say a bit, for the summer, I don't think that number.
We did the thermal analysis, including the summer. The paper is, I will send you the paper if you like. Yeah. So it's basically what was say. So, and this is actually thin film at 20% efficiency. Okay, so it's basically what you need to do. So I'll send you the paper to look at that. So implication for facade and for aerodrome. We can also send you the transist model if you like to look at it. Okay, so going down into wind energy for the urban environment. Remember this diagram here, if you wanted to have a zero carbon building, you need to utilize the surroundings of the building to generate more power for you to make it zero carbon. Sunlight, wind, ground source, and whatever you can have. And these are the turbines that are promoted for people like us, domestic owners of buildings, to generate power from and roof of your buildings. In 2003, we had a research program to analyze the output from these turbines. And we came up with some real interesting graphs to show that these turbines on the whole were not really produced what's being given or predicted by the industry that's being given. And the reason for it is really related to the power curves that they have and the way it's optimized. And these are sold by retailers. For example, we have a retail company called B&Q, like a warehouse type activity. You can go and buy it for £1,000. And because you want to do something for the environment, you buy it, put it on there, and you find yourself not actually displacing any power, not bringing any power in. So because there is a lot of uproar about this, UK instigated a UK trials of these wind turbines. And this graph shows the turbines that we have monitored, or some of them are monitored, about 80 of these are monitored. The white dots are looking at the 1 kilowatt type turbines, and the red dots are the ones about 5 kilowatt, 4 to 5 kilowatt turbines. And we did all the analysis for these monitored turbines. And this is the graph for these type of turbines that you have. You can see the wind speed, and you can see the annual energy per kilowatt, per meter square of swept area. And this is the Swift, which is this one here. It's actually, you can see that as you go further to getting wind speed of about 3 meters per second, you don't get very much of power being produced. You go up to that, and the curves are not really the normal curve you expect from wind turbine, which is go up like this and like that at a peak value. So these are the actual curve that we got from monitoring these turbines. And we brought this to the industry, into the government, saying to them that these power curves had not been released for the public to actually see what's happening. And you can see that you need to get up to a wind speed of about 6 meters per second to get something very close to what they claim. And you don't get that very often in an urban environment. Anyway, so we did quite a lot of analysis and work on this. And the government released the report, and most of these companies actually, in fact all of them went bust because they returned the equipment and so forth. But the data for other turbines, which are bigger, okay, gives you a very nice power curve and so forth. And these are an open environment, or by the sea side and things like that. So you got wind speed about 5 meters per second, then you can get enough power to actually utilize it. So we proved that these are okay as long as you have enough wind speed, but the other ones are really not the right thing to utilize. Any questions on this? Okay.
Isn't there anything like rated power and rated conditions for measuring that power?
Sorry, there
must be a rated power output for these wind turbines.
Yes. For example, here is a 5 kilowatt. So this is the rated power here for this one here, which is the Elotex. You can see this is the power curve for that. Get to the rated power at 10 meters per second, and it stops and things like that. And then the starter speed at here at about 4 meters per second, and so forth. Okay.
The rated power is measured at 10 meters per second.
Yes, at 10 meters per second. You always get that. For example, large-scale wind at 12.5 meters per second. So it comes up to the rated power and it stops. It doesn't produce any more power. Because if you wanted to produce more power, then you need to have better infrastructure like gearboxes and things like that are included.
I agree with your finding that it makes no sense to have the micro generation at very low hubs in the cities, right? Because you don't get good wind. But I mean, how is this comparable? Basically, what you showed the British power curve and this one, because obviously these are different sites. I presume that if you put the other turbines in this hub and in this location, you would still get a much better curve. Right? So
you can see that going up even to 8 meters per second, you don't even achieve the rated power of about 1 kilowatt. So these turbines themselves, they've got also an inverter in there, where if the wind is not blowing, it actually is taking power from the grid itself. Unlike photovoltaics, when it's dark, it just stops, right? So you got, there are some graphs. There's a paper actually that I can send you that. Actually, there are 4 papers in there. Some of them actually taking up power from the grid rather than actually producing power. So you can see from this, they are not designed really properly. That's basically what we said. They're not designed for the purpose that they're supposed to be designed for. Okay. So again, here are some homes that we are monitoring from 2005. This is about 10 houses, highly insulated houses with solar thermal, with photovoltaics in there. And I just wanted to touch base in relation to behavior, because people don't really understand when the solar resource is coming around. So this is what we measure in relation to the output from the solar cells. You can see it in the UK. You've got this bell-shaped curve, PV generation. And here's the consumption from the householder. And you can see it starting at about 6 o'clock, peaking at school time, before school time, and so on. And then they go out to work and come back again. You get that. And then you got the export to the grid, which is the red curve here. Okay, so most of the consumption, most of the power produced by the solar cells is actually sent to the grid, which at the time was about 4 pence a kilowatt hour, while the household actually buy the power at about 8 pence a kilowatt hour. So what we advise them to do is actually to try and make sure that they shift the loads, for example, in their washing machines and other loads, to where the solar resource is highest. Then they displace importation and also get the funding for that. And there are some papers to prove this areas for behavior. And another thing about behavior, this is in San Diego, which I visited not too long ago. And I was walking from my hotel down to get, I think, the train. And I passed by this house here. You can see this chap is trying to do his best for the environment by having photovoltaics, yet the vehicle that he drives is 6 litre. And it's basically what really is driving people in relation to what they have to do. And in fact, this person may have something else which is other than what I have seen. Maybe he needs to pick up loads somewhere else, and also because public transport is not very good, people have to have cars and so forth. And now I'll switch to something which is up to really my heart. I like to do quite a lot of it, which is solar-powered camels. Let me smile at that. Okay, this picture is around for a long time, and actually was something that was advertising solar power in remote areas in Africa. This is a guy from the Tuareg, 2 PV panels, a solar fridge, and the batteries up there. So these guys went around the desert, 60 kilometers with the camel, actually holding vaccine at 4 degrees centigrade by solar power and vaccinating those villages. But I don't want to talk about this. I want to talk about something else, which is energy for development and how to invigorate communities, rural communities. And these are the projects that we're currently running in Africa. And from my experience, you get a lot of people, either external donors or people who want to do quite a lot for developing the local communities by having investment. Either it's coming from these donor agencies or from the local government. And you have community-based activities. And then you need to get some training and the revenue. In my experience, most of this is not being done. And for us, we need to do a sustainable scheme, which is replicable. And that, to me, is what we have done in relation to the community, energy, engagement, and so forth. Most of these steps here are done without having this training, without having the revenue generation. Quite a lot of these projects in rural Africa and rural Philippines and other Latin American countries actually failed. So we need to do design for sustainability, and the community is the key for that. So what's our approach? Energy for development. Set up a local cooperative, make them members and be part of the management, and develop financial setups for how you want to make the project sustainable. And then you do technical design, look at the resources, the sites, and so forth. If possible, and it's an arid area, you want to do rain harvesting, and then you have connectivity to the community. Okay, community is really at the heart of it. Once you do, you need to do a technology installation. You want to do it as quickly as possible with the cheapest and much economic way of actually delivering it. You need to have some sort of financial model to forecast the energy income and also the connectivity to the region. And the cooperative financial management, you need to have that in place from day one. So that's the approach that we have. And then you look at the social impacts, healthcare, education, businesses, opportunities, and so forth. So this is really in summary, and I've got some leaflets in here which I can give you later on to what we're trying to do in energy for development. And we selected Kenya to start with. We developed a whole country GIS system to allow us to understand where the people distribution are, where the villages are, where the health centers are, where the roads are and going, where the grid is going to go, and where the grid is, and so forth. So we have that in relation to all the Kenya activities that we have. And then you're looking at ways of actually using that information that you need when you want to have an intervention for rural communities. So looking at excluding areas where the density of the people is less than 50 per kilometer square, and you exclude areas where they are closer to the grid by 15 kilometer. So understanding the region was one of the things that we had to do for about a year or so to understand what rural electrification is like in Kenya, where we can make improvement, and does our approach in energy for development in relation to community engagement will be a winner or not. So we tested this. We have quite a lot of social scientists who work with us. So we did 2 surveys, what's called a needs survey, quick survey going around some 12 villages in the regions we have selected, and then the baseline surveys which included health, included education, you look at maternity and so forth, and that actually addresses some of the Millennium Development Goals, so it sits at the heart of the project. So design for sustainability, so we created an energy service company with a mini grid. So this is the structure that we have. Basically we have 2 containers with everything that we needed shipped from the UK, and we connected the installation and the businesses that I'm going to talk about in a minute with about 7 days. So we have a trading center or a village center if you like. You connect the schools, the health center, and the churches that they have up there, and then you connect directly the businesses and you meter them. Okay? And you have all this type of commerce actually developed, like solar lantern charging as well as mobile phone charging. And because you're connecting the businesses, you need to also think about people who are remote from the business center. So solar lanterns, LED lanterns are really things to go for. So we had provisions for selling LED lanterns through the community itself. So they buy the lantern, they can charge the mobile phones as well from it. So you generate businesses within the businesses. So you invigorate the whole village. So we connected 40 churches, 40 businesses, including schools and so forth. And now we have a target of 500 households for lanterns and so forth. We have actually now the charge that the community charge themselves for that. And that's actually an advantage to have a remote power. Okay. Yes, I got some a leaflet in here. I'll give you the leaflet in a minute. Okay, I'll go to something different now. You all seen this? This is a trailer that transports refrigerated perishable food. You could have a frozen section. You have a section for basically yogurts at 4 degrees or maybe less, and another section maybe for bananas at 13 degrees. So, as a company called Saveways that we worked with, and they have these trailers which they can go on a car or actually go on a train. And quite a lot of the material that they have in there, or the goods that they have in there, have got very high value. So they come in from the south of Italy up to the north of Scotland, multimodal trailer system. And these type of generators, this type of refrigeration has got a generator, a diesel generator. It could be actually underneath there. It's got a battery in there. So they have a problem in that many of them, they have a flat battery, right? Because they're sitting there for about 3 weeks, and so they have a flat. They came to us, say, what can we do? So we installed a small panel, about 30 watts on the top of that, just to trickle charge the battery. So they have security of getting the fridge to turn on straight away from day one. But what if you replace this whole thing with solar panels? This is what we done in 1997 with this type of system. And here's a bigger picture. The battery is down here. You got the radiance sensor there to tell you how is it doing, and you got the monocrystalline PV modules that we have to buy to fit in the roof of the trailer. This is a standalone system, and actually operated where the conditions. So this is a major condition. This is the design or predicted conditions where there is really very hot in the UK. I have some graphs to show that, but I didn't put them in here, which shows that this actually works extremely well for a UK environment, because when you need the power, you got more sunlight. When you don't need it, you don't worry about it, right? So this is just for refrigerated, 4 degrees centigrade, not for frozen, okay? So we went in and did a lot of work on the design of the whole trailer, the insulation system, the fans that they have in there, looking at regenerative brakings and things like that to actually augment it. A lot of work done on this, but unfortunately Sainsbury's, which is one of the big retailers in the UK, franchised their operation for the delivery vehicles. So became smaller companies who are not really interested in sustainability. So we abandoned this. But it's something really quite interesting to think about.
But now with much cheaper prices, will it pay for itself somehow?
Yes, the cost of this one, we actually had to develop the fridge as well at the same time. The cost for this and the fridge is about twice that of the normal, the one I showed early on was twice as that. But that's at the cost of about $8 or $6, and now it's about $1. So it's actually quite. So it does make sense, but it all depends on the ambient temperature that you're dealing with, rather than just. In the UK, it really works very well. That's something that we did quite a lot of work on. Question?
And just because in Dubai they are trying to have air-conditioned bus stations.
They have them now.
They are facing difficulties. I don't really know what the difficulties are, but I don't know what do you think with regards to the same technology replicated for bus stations?
The service area for the bus stops is not enough to produce the cooling required, especially in the summer, in my view, but you need to do the analysis. This is 4.5 kilowatts, by the way, so it's just smaller modules.
This is a 40 feet container?
It's a 40-foot container, yes.
But it would still work for a 20 feet container?
It will work for it because you got less space to cool, yes. But it depends on the ambient temperature that you're working with, right? Because here the ambient temperature goes to about 45, 50 degrees and becomes very, very dirty. So once you open the door, then you lose quite a lot of cooling that you have in there. I've got really some nice graphs to show you, so there are some papers as well being published on this. And now for something different, very different, which is now going into the megawatt scale of things. I've got some videos to show you. This is tidal stream energy. Here's a turbine, open hydro. And this is a wave energy device. It goes up to about a megawatt. This is 750 kilowatts. Sorry? This is the Pilamis. Basically, it's a cylinder with the joints between them, and as the cylinders go up and down or sideways with the waves, it compresses a liquid in there, and that liquid the compression is accumulated through an accumulator and drives the turbine. Okay, so 1, 2, 3, 4, in fact, now they have 3. So it's anchored at the front, otherwise it would be taken by the sea, but allows to move along with that. And this is a tidal turbine. Basically, it's the flow in the sea, like wind turbines, and rotates this rotor in there. Okay, I selected it because it's not the horizontal axis turbine. So we're doing quite a lot of work on this within my group. And basically, we're looking at all aspects of this, looking at the resource, looking at whether it's wave, tidal, or maybe ocean thermal energy, looking at the converter, and looking at the demand. Complex and challenging system and an environment which really regards respects, okay, which is the sea. Really important things to think about all this in relation to either device development or project development. Now I'll talk about that in detail. So things to think about is if you have a specific device, if you have this brain idea, a thought, or something quite unique you wanted to exploit, the things you want to think about is how you capture the energy, how you take that power, how you control it. Is it electrical or is it hydraulics? How you transmit that to the grid, and how do you fix your device, importantly, within the sea rather than being taken out by the sea. So these are the specific things that you need to do about the device. And then you need to do a bit of economics. You're modeling what's the energy price, because without that you don't know whether it was a brilliant idea. If it's going to cost about 4 times as much as we pay for electricity now, you may find it difficult to sell the concept. So assuming that you've got a device, then you need to think about specific projects, and these will need to look at site resource analysis. How is the resource interact with the device? And you need to think about who else used that area of the sea, so you need consent and permitting, looking at the instruction, the layout of the array for the device, and then how you're going to deploy, maintain, and also take it out, decommissioning it. Quite an important aspect that you need to do. And then you're looking at the environment and the environmental impact that you need to think about. And then again you go ahead and you do some modeling. You include in that the insurance, the finance that you need to have, the vessels, where are the ports that you're going to go from there, and also the grid, whether you have consent to connect to the grid. And then you look at the people and safety thing, which are the other impact. The stakeholders, for example, we have a project in the south of the UK, and been announced only last week that we're going to have about 20 megawatts of these devices by the Isle of Wight. A lot of the fishermen were extremely unhappy about it because you got a lot of crabs in that area, okay? And I think it's just because education is not given to those fishermen, and they think this crab area will actually be impacted on. So we need to educate these people, look at the risks, for example, the livelihood risk as well, and where the infrastructure is around, for example, ports, and also the technical capability of the team that you have. You don't want to be relying on somebody else if you're going to develop this. So these are really important areas, and they are in the paper that I published just recently, if you want to have a copy of that. And you look at wave energy. Wave energy has got, this is basically characterized by the shape of the wave. You can get a crest, and you got the trough of the wave, you've got the wave height, the length, and the amount of energy in there is about, in the first top layer of the waves. And the power in there is related to the density, the acceleration to gravity, the wave height, and the period. Basically, it's related to the wave half square and the period. And this is really an idealized solution for monochromatic waves. The waves are not just coming from one direction, they're coming from different directions. So you need to think about that. So they have got patterns which are irregular, both in amplitude, phase, and directions. You need to think about it. And there are always probability of extreme waves and hurricanes that you need to have. So if you want to have a device which is actually in the sea, you need to think about whether this device will survive. And the peak power is generally available in deep water, so you need to go as far away from shore as possible. Another really quite constraining environment is that you get frequencies about 0.1 hertz, and our grid is about 50 hertz or 60 hertz. So you need to, if you want to connect that to the grid, you need to think about ways of coupling this up through your accumulators and things like that. So I showed you the Pelamis early on. But there are many devices that are contemplated, in fact, a lot of devices that are not currently being developed and actually thought about. For our work in Southampton, this is related to the resource. This is related to the power of the Pelamis. We did a lot of work with the Pelamis. The Pelamis itself came to us and they said, we'd like to know how we can get a quick data on the resource if we want to invest in an area, let's say New Zealand, and something like that. And you got satellites going across the world, and there's a 25-kilometer separation, and these satellites give you, these altimeters give you some data for the wave height, but not the period. And this is really the power that you can get out from these waves across the UK. So you look at the altimeter data, you look at the accuracy of that and combine that with some data that you can validate the work from Boy's data across the UK. So we did some analysis for the Pelamis, and this is the devices. So we did some work here in a place called the Wave Hub, and here we go. This is the percentage of annual wave energy you get, and you can see for the Pelamis, quite a lot of the energy you get is really related to where we need it. Not in the summer month, but in the winter months. Okay, so they developed this now into a package themselves that they utilize wave climate, which you can download, which are free available, and then you can utilize the Boy data, which they can buy, and they combine. So they go to a separate site anywhere around the world and say, here's our devices. You can buy 10 of these. This is the energy yield you're going to get for the next year or so, or maybe 10 years, we want to do that. Here are some of the conversion devices. This is a device for a university in Sweden, Uppsala University. This is a linear generator inside, and these are the buoys. They go up and down and move the linear generation inside that device. Okay, so there is a talk that this company, I'm actually working with them, it's called Sea-Based. There are quite a lot of videos about this, animation videos. I didn't get one down. This Sea-Based company wanted to actually utilize this for also desalination. Okay, so it's quite interesting that they are trying to explore this. And they are deploying at the moment 10 megawatts of these devices in Sweden. Okay. The next one is Anaconda. This is something that is not invented in Southampton University, but we worked on the hydrodynamics of it. I will give you a break to listen to a video. Why do we have a... Whoops. There you go.
The Anaconda wave energy converter uses an entirely new principle to convert the energy from long ocean waves into electrical power. The machine is moored at the bow and can swing so that it will remain head to sea. The bulge tube is completely filled with seawater under low pressure. As the sea wave passes along the tube, a bulge wave is excited, which moves in front of the wave crest. Energy is captured continuously from the sea wave in the region of the bulge, and diffraction replaces this energy as the wave progresses. At the stern of the tube, the power takeoff receives the bulge wave as large pulses of water and smooths the flow before passing through a turbine generator. It is then drawn back into the tube during the reduced pressure phase of the bulge cycle. Anaconda wave energy converters will be grouped into farms of 20 or more machines producing over 20 megawatts. Each installation will have a minimal environmental impact, being situated beneath the surface in deep water, well offshore.
Okay, so any questions on the Anaconda? It's quite an interesting device, actually made of a rubber tube, very simple, filled up, half filled up with water, and it's the water in the side that is compressed by the wave to produce this bulge wave. A lot of variation of this type of device currently being worked on. A lot of things that are required for the power takeoff, very challenging, but it's actually a commercial company now developing it. Questions?
Who studied its effect on the sea animals?
And I don't, because it's a surface mounted, the sea animals will see it and they'll move away from it. There is nothing rotating at all except this big tube going up and down.
The question is how to define the place that has the most potential for that energy, or have any technology or just find data?
Actually matching a device to a resource is quite an interesting subject as well. So a lot of people, for example in the UK, we're interested in wave energy because we've got intensive areas around the west coast of the UK. And these are the areas where you get the high waves and things like that. And you need to know to go further away from the shore to get the bigger waves. So you need to map the resource and actually match it to the device. And this analysis can be done, yes.
So I presume this is to be used in these oceans where, I mean, for example, the state of the Hormuz or the Gulf, Arabian Sea which comes in, it is quite calm. To the ocean near Yemen or some other.
Well, I think in Yemen you'll use these, but not in the Strait of Hormuz because you've got a lot of shipping going there. So you don't want to block the shipping. Remember, these devices, when they operate in this, they actually have a footprint which you have to stop any boats or anything like going around it. So you have some beacons to give warnings and things like that. So you take that footprint, so you block everything else that goes around it. A question? Have I answered the question? Okay. So here are some contraptions of wave energy devices that are currently being thought about or being built. You got another more. And basically what I'm saying is actually it's infancy. Although there are some, especially this device, there are some devices in the sea. They are at the prototype commercial stage, but the development is progressing. So if I go into tidal stream energy, which is really quite interesting for us in the UK. And I don't know whether you're familiar with this equation in wind energy. Okay, you got the power, half rho A velocity cube multiplied by CP, which CP is the power coefficient. And if I actually do this as well, so this is actually applicable to wind turbines as well as tidal stream turbines. You're looking at the flow in the sea compared to a flow in the air, And the flow in the sea is really restricted by what's called the bathymetry, the depth, and where the velocity is highest. So for wind turbines, you'll be operating within about 25 kilometer of space. And for tidal stream energy, you'll be operating from 50 to 100, maybe 150 meter depth. So you need to utilize these things in a way which is actually quite important. The other important factor between wind and wave is this factor here, density. Okay? And the density is about 800 times that of air. Right? So the power increases by that amount. And here's a graph to illustrate this aspect, power density in kilowatt per meter square. Here's the velocity for wind turbine. Okay, so let's assume a wind turbine is rated at 15 meters per second. You can see that the power from wind is about that. It's about 4 kilowatt per meter square that you can get from it. If you look at tidal stream energy, which is rated at 2.5 meters per second, which is actually where you get quite a lot of intensive areas, you can see it's almost double that. And that's really due to the fact, actually more than double, due to the fact of the density. And because you're operating in a buoyant area, you've got this property that you don't have very much to worry about. Important things to think about is actually how you anchor it in the sea, because as you'd expect, this will also have a thrust forces on the turbines themselves. There's flow in there, so you need to have stronger foundations. A lot of work being done within my group. Here's the UK. Here are where the resources. I talked about the Isle of Wight. Resource in Scotland, which is predicted to generate about 10% of the UK electricity supply. Resources in the Channel Islands, resources across on the Bristol Bay, and other resources around the west coast of the UK. That's tidal stream energy. Remember, it's not tidal barrages, it's nothing to do with height, tidal gauges. So this is the program that we started to do, actually modeling, hydraulic modeling of this channel ourselves in the UK to actually understand what will happen to these turbines. So you've got a forcing coming from the Atlantic of about 120 gigawatt, and you've got a dissipation within the center here, which is about 108 gigawatt, and you've got something going on across towards land, and then coming out through there about 16 gigawatt. Okay, if you define your operational area and you mesh it out into a CFD model, you can zoom in into areas like this and actually to understand how much the resources are and how much you can generate. Here's a simulation we did somewhere at Portland Bill. Actually, this is where the Olympics, the sailing for the Olympics happened. So this is, these are the graphs of how the flow appears in here, and just look at the direction of these flows.
So what are the colors representing?
The depth. So we have a design for a 100 megawatt type array in here that we did, and that's currently being the local authority in here currently being interested to look at that in detail. Oops. So these are the type of arrays that you think about. If you're going to have a similar structure, which is basically a pillar or a pile, you want to pack it up with as many turbines as you need. Okay, as you can do. For example, here it's carrying 2. You could have 3, maybe 4. But you need to think about interactions between these turbines. You need to think about the wake effects that happen between the turbines and how you space them out. You need to think about the bathymetry. You need to think about the waves. Okay, so we've got work looking at these issues in relation to channels. So we have model channels that we have in the university, which we put some profiles in here to allow us to give some turbulence. We instrumented the blades, and we look at the bending forces on the blades and the power takeoff and so forth. And we also measure behind the turbines. And you have simulators in the labs for example, actuator discs, 10 or 8, and you set them up into an array and look at the various flow conditions that go around them. And here's a simulation we did for Portland Bill. This area here I mentioned earlier. Here's what the predicted, I can see here's the velocity in that site, 2.5 meters there, going down to about 1.7 meters. And this is the velocity cube, which is related to the power. Okay? And these are the bins for these velocity cube. And this is the time in hours. 2006 and 2016. Now how can we, I mean, the tides are predictable within 20 minutes. Okay? So that means the power you're going to get is actually very, very predictable. And you can use it as basically base load if you are really clever about it. And if you have arrays around the UK, for example, which are at different phases, you can actually do quite a lot within the grid itself. So, 2016, I said the things are predictable. You can see here the power. 2016 is much higher than that. And anybody tell me why? Right. So how do the tides come about? Mainly the moon, right? So it's the moon. So this is really the position of the moon, being closer to us. So you've got the pull that's higher, and that's what you get. And this is what you can get with this type of activity, which you can never get in any other renewables. You can predict as far back in the future as you can in relation to the energy yields you can get from these arrays. And that's why it's so interesting. A lot of people are interested in it because you can predict the energy yields, and you can predict with confidence what the payback will come in and also what the income will come in for your company. And here is quite a lot of these turbines. The majority of them now are actually horizontal axis turbine. They should have been animated, but I think it's going to be quite long to do this. So this is a horizontal axis turbine in here. There is one blade of some of them in here, but different configuration. This is a floating device with horizontal axis 2-bladed turbines. This is also 3-bladed turbines that we have in here. So there are about 5 of them currently being tested at a megawatt, 1.2 megawatts. One of them in Northern Ireland. The other 4 are in EMEC in Scotland, in northwest of the UK, northeast of the UK. Okay, so there is a group of companies trying to develop arrays, and by next year we'll have the first 10 megawatt array in Scotland. Again, it's really still in its infancy, but there is development in the technology and it's progressing. Any questions on this?
Do you know what's the cost now for
the predicted cost for tidal energy is about 4 to 5 times that of offshore wind, right? And actually maybe less. For wave energy is about that actually. For tidal is about 3.5 maybe to 4. Wave energy is even more. There is a report about the Carbon Trust which gives you all the costs in terms of kilowatt hour. I also got a presentation, but I'm taking a long time but I can talk to you about it and just send you some details.
So that's capital cost, right?
That's the capital cost, yes.
How about the emissions?
For operators, actually that includes some operations and decommissioning costs within that per megawatt. Same as offshore wind. You have is deployed costs and decommissioning costs within that megawatt. In the UK, you have got what's called the support mechanism, contract for difference. It's 5 times that as much as you get from offshore wind. Okay, really a huge subsidy that we have for these technologies. So here we are today. This is the first array, 2008, done in Portugal. Unfortunately, that stopped action because the company that bought these turbines, Palam's turbines, went bust. This is the marine current turbines, now it's Siemens, bought by Siemens. in Langford Lough in Northern Ireland, 2-bladed turbines, and they have a plan for 10 megawatt in about 2 years' time. And these are first generation devices. So the cost reduction is appearing as we go and as we deploy more. So this is the plans for by 2020 in the UK, in Scotland, when you have 1.6 gigawatt by 2020, 600 will be wave, 800 will be tidal. And here are the areas where you can have these devices done. I picked it up from The Guardian. They show the sites and they show the technologies that you import in those. Here are the technologies. So the Polaris are number 1, which is in here, and the Oyster is number 2, which is in here. This is basically a flap that goes up and down with the waves and things like that. So this is supported by the entity that owns the land or the offshore land around offshore or the shoreline around the UK, called the Crown Estate. The cost of the technology is roughly been about 4 billion, so you just do the sums, about £4.5 million per megawatt. And it needs to have infrastructure, basically grid, support, ports and things like that, which is about 2 billion. Okay, so this is the ambition by 2020, unlikely to happen, and this is my view.
2 small questions. Can you explain why this is less variable? And secondly, what about maintenance?
Sorry, what do you mean less variable?
You said that this the
Tidal?
The power output is less variable and it can be used as base load.
Because the tides are very predictable. You know when the sea is going to come up, when it's going to go, and actually driven by quite a lot. So you know that flow in the sea with a good action.
Over 24 hours in this?
You know every 20, yes, you know how it varies over 24 hours. Every 14 hours actually it varies. You know that for the velocity, and you know that for the height as well. So, and that's why it's very predictable.
And maintenance of these structures is this important?
Yes, the maintenance is one of the important issues. Relation is basically, for example, this device here. To maintain it, there are hydraulics, and you just push this up to the top surface, and you can pull this out. Okay, some devices actually the whole thing comes out, and you pull it away, put another one in. So you do the maintenance away from the sea. Okay, now I'm going to talk about something else, which is energy efficiency. And this is basically related to what the UK is trying to do in terms of consumption, energy consumption. And I'll be talking about, this is basically the total data for the UK, terawatt hours, 796, including heating and electricity. And what I wanted to is actually the graphic shows you that the urban and the towns is where most of the emissions happen. Okay, this is the total for the UK. The total for the UK. Okay, so if you wanted to reduce emissions, you will actually apply a lot of work to the cities and towns, basically our buildings and our transport systems. And here's what the target by the Energy Act. These are the current emissions. We need to reduce that by 2030 by 34%, and by 2050 by 80% for the UK. And you can see this is the urban and towns that need to have the reductions in. And here's the GIS we done for all of England. Scotland, we assume, is already independent, so we didn't put that in. So you can see this data is coming out from 3 databases, DAC data, and also coming out from the National Office of Statistics. And we have 3 cities that we are looking at: Southampton, Lancaster, and Birmingham. It's called Livable Cities Program. And we are employing quite a lot of work in relation to emission reductions in these cities and developing tools to allow us to do refurbishment at scale. So this is the energy consumption per, actually it is the energy consumption per person in terms of CO2. The other one, what's the other one? That's the CO2. This is the energy in kilowatt hours per, right? That's what I'm looking at. So basically you've got this data. You can zoom in any city, any town in the UK and actually find out what a village is doing and so forth. So here's the cities that I mentioned. Portsmouth also became a later addition. And this is industrial, the red one, industrial, the blue one, which is electric. And the domestic side is these sites here that we have.
I don't understand this graph is, why do you have the axis around zero?
Because I've separated out the domestic as well as the industry. Right? This should be really positive.
Yeah, it should be positive.
Yeah, right? It's just Excel can allow you to have positive, right? So this should be really positive. So apologies for that, and well spotted. Okay, so I'll talk in detail about Southampton, right? So basically these two cities are almost similar because they are by the sea. See, Lancaster, which are in the north, is higher than Birmingham, okay, because the heating is higher. And these are the reductions. I'm not going to go through that. Again, what's required for the various cities that we need to do. So here's the plan, the master plan for Southampton City. Each number here is actually a project that the city wanted to do. Southampton, we've got a lot of water around, yet we don't have a waterfront, because the best part of the waterfront is taken by the port. Okay? So there's a big tension between the city and the Port Authority to try and exploit it. So this is an area where the city wanted to actually exploit, and this is likely to happen in the next 5 years. This is something that we're working with. You see the football ground, Southampton football team. Now they are one of the top teams in the division. So we're trying to exploit with them. These are really industrial sites here, junkyards and things like that. And the waterfront is really spoiled up by these things. So what we're trying to do is, everything what we do is to think about the master plan for the city today. It's a $3 billion investment over the next 20 years. And basically a link between the data, between the knowledge base with the universities and the city and businesses. So here's what Southampton footprint is. 2005-2011, we have a reduction in our emissions by 11%. And these are the various components of the emission reductions that we achieved by 2010. So the various components around. So in a meeting with the City Council last Friday, we have the biggest consumers around in the city, and it is now mandatory for them to report their consumption, energy consumption, to the city. So anonymize it and actually say this is what the city is doing, and that actually is part of the activity that we're working with the city. We also have what's called the Energy Company Obligation Scheme, which is basically a scheme on the utilities to support hard to treat properties in the cities. For example, those are solid waste and things like that. And that's actually an income related to carbon that cities could apply for to get that money. And we have about 16 eco regions in Southampton. These are the lightly colored blue. And these regions contain about 15% of Southampton properties. And this is the type of properties that we're thinking about, basically 1960s and so forth. And here's one area that we're looking at, which is Woolston. So we're mapping that in the GIS. We're looking at individual housing. So each dot in here is actually a property. So when you click on the GIS, it gives you the details of the property. It gives you its energy consumption. It gives you when it's built and so forth. And that data is being captured in the GIS, and we do some analysis on it. And here's some details of some of the, in this eco area called Woolston. And you can see the energy consumption is going down. An interesting graph here. It shows that the cost of gas is almost static. Okay? Yet the consumption stayed static. The cost of gas has actually gone up now, yet the consumption has gone down. The reason for this is that these people living in these areas are very poor, so they can't afford to heat up their homes. And that's really the major reason for it. And that's why Eco scheme is coming out to actually do that. So we have Also district heating in that, which could be expanded to other that. Contracts finalized about £30 million. But there is a change in policy done by the Chancellor last Christmas, which made the cost of carbon go down drastically. So the viability of the scheme is now under question. So this is what we deploy in our methodology, is we obtain a lot of data on the footprint, on the GIS, looking at the number of floors per property, the age and the type. And we look at the areas, total floor areas, the windows, the perimeter and the wall. So that's all done in software at each individual property. And then we estimate the number of floors and the number of properties that we need to apply it. And then we have in software interventions for these. First intervention, you apply floor or roof insulation. You change the window or actually have a wall insulation. So you do that, you run your model with the current technologies, you validate it because you have data. We've got 40% of the data on the houses of Southampton. And then you come up with energy savings and emission reduction scenarios based on technologies that are currently available. Okay? So you do that at scale at the whole city, and we do it for across the whole of the 3 cities I mentioned. And then we have the social scientists who come in here, who will tell us what will happen to the demography, what will happen to the people in the next 50 years, or 40 years now, and looking at the well-being, the attitude, whether it's going to be acceptable and things like that, and we apply the softer measures to that. Okay, so the impact of actually having to do this wall insulation comes into play, whether it's going to be acceptable or not. And then we look at policy drivers, and this is a research challenge within the project that we have, looking at environmental drivers and look at the policy implications. We add this all up to give us this reduction in emissions for the whole city. And then you repeat the analysis by other interventions, for example, district heating, have the buildings to generate power and so forth. And looking at the changing climate, or is it going to have a 2-degree temperature rise, 4 degrees temperature, or 6 degrees temperature, because these buildings will be around for the next 100 years. And that's why you need to play around with that. And then we go again and do a number of iterations. Can't remember what I did there. So this is, and then we look at radical engineering solutions, future technologies and so forth. And this is where we're looking to Mustard to tell us what future technology is going to happen, right? So it's actually future gazing, okay? Whether facade engineering that we can develop be much more appropriate, it gives you all the properties for insulation as well as for generating power, and perhaps directing sunlight into the areas you don't need to have these lights to be on, and hence reducing your emissions. All these technologies have to be come in play. Maybe we won't have any offices. Maybe the internet is so fast that we can go to our health club and just do our work from there, so that you reduce the number of offices that you need to have. All these issues are going to have to be delivered and thought about. And then the prize is how much you can achieve in that reduction. So looking at slices of emission reductions as various interventions, and then coming up with a policy to the government saying, this is what we can do. Can we achieve that 80% emission target by 2050? And how bad it's going to be, how much it's going to cost economically, and whether it could be achieved. And these are the sort of issues that we're trying to do here. Here's the first part of the work. So these buildings, so this is a clad of those buildings, so they've been clad, insulated from the outside. So we know the details about them before and after. We measured before and after. And here's the simulation from the package. And we can see that by these interventions, we can achieve about 50% reduction in energy consumption in those buildings. That's just by hard interventions. Okay? So we're validating our models in relation to this. And then we're looking at ways of, this is the feed-in tariff for the UK. This is what, when it was announced, planned to do it, and then the government said we can't afford it. So this is the income per kilowatt hour from a feed-in tariff. Started at 43 pence a kilowatt hour, and now it's gone down to about 18, actually now is about less than that, it's about 15p, 11p kilowatt hour, because that is unsustainable, the government can't afford it. So buildings are generations. Southampton got about half a megawatt already installed in all buildings, so that gives them money at this rate, right? So they use this money for doing refurbishment. And here's the buildings I showed you before, where PV is on top of that. You have a PV field here, and so forth. And they were basically, for in our assessment, we need to only design for the right orientation, south facing and so forth. And we look at the business case for all the properties in the UK. I mentioned this before, connecting people to energy. So, I'm almost there. So, I hope I gave you a flavor of about kilowatts to watts to hundreds of watts and megawatts and so forth in my talk. And I hope I gave you a flavor about what we do in Southampton in this. What I really wanted to say is, rather than saying thank you first, is to say I was here in this country 24 years ago negotiating with the Ministry of Energy and Water and Energy about having two institutes, one in Southampton and one in Abu Dhabi. And I spent about 2 weeks negotiating with the ministry. And it came out that it could have been really worked and funded where we can have direct classes both done at Southampton, which I've listened to here and here in Southampton, getting linkages and so forth. Unfortunately, the funding required for Abu Dhabi was available, but the funding required in Southampton was not available. So that scheme did not work in Southampton. But now I'm really pleased that after 24 years that there is an institute here called Master, and that you guys are here to actually be there in that institute. It was my aspiration 24 years ago to have this sort of thing. But more importantly is that you are here, you are the younger generation, and you are the people who are going to change the world. So you have a huge responsibility in you. And I hope today I gave you some indication about what could be done. And obviously it is what is my experience over the last 30 years in this area. And I wish you luck and thank you very much. You can ask more questions if you wanted to.